Hello again, physics friends. Today we're going to focus on the basis kets or basic states of a quantum system. And we've seen already what happens if we have the following two experiments, right? We have a Z analyzer in both cases, followed either by an X or by a 10-degree analyzer. In both cases, we have this intermediate state, which we found we could write either as plus in the Z direction, because that's what it is, right? It's an atom that just came out of the plus port of a Z analyzer. But we found we could also write it as 1 over root 2 times plus in the X plus 1 over root 2 times minus in the X. And that was acknowledging the fact that if you shot 100 atoms, if there were 100 atoms in the intermediate position, that you'd have 50 atoms exiting the plus and minus ports of the X analyzer. So the probability of exiting plus X or minus X is 1/2, and these amplitudes here squared give that probability. So 1 over root 2 squared gives probability of 1/2, 1 over root 2 squared gives probability of 1/2. Similarly, we saw that if you had 100 atoms in the second experiment entering the second analyzer, instead of 50-50 odds, you would find 97 and 3, so 97% chance of exiting the plus port. And in that case, the states at the exit would be plus in the 10-degree direction and minus in the 10-degree direction. So we said we could also equivalently write the state in the intermediate position as, let me stick with black here, as square root of 0.97 times the state plus 10 and square root of 0.03 times minus 10 degrees. And let me bring this all back into the page here. Okay. So we have three ways of writing the same state: a definite state in the Z direction, or a superposition in X, or a superposition in the 10-degree direction. And all three are representing exactly the same atom, so they're all equivalent to each other. What we say, the language that we use to describe this, is that this intermediate state here has been written using three different basis states, okay? And in particular, we have it written either in the Z basis, or we've written it in the X basis, or we've written it in the 10-degree basis, okay? And we're free to choose any basis that we want, but we're just here introducing the term basis, and that means what kets are we using to describe the system. Here we're describing it using a Z basis, and we find that we're in a pure state or a definite state for Z. In the second example, we're using the X basis, and we find that the intermediate state is a superposition state of X. And in the 10-degree basis, we are also in a superposition state for 10 degrees. And I just wanted to take a moment here in this video to talk about the kind of a geometric analogy for what these basis kets or basis states are. And the geometric analogy will be, we'll look at a regular old vector, an arrow in space, and we'll look at a two-dimensional space. So let's take the following scenario where we have, actually I'm going to start a little bit differently. I'm going to start with a vector, and we'll call this vector the A vector. So vector here is nothing more than an arrow. It has a direction and a length, okay? And this vector is a thing that exists in and of itself. We can choose to describe that vector using a specific coordinate system. So if we'd like, we can draw on top of this picture a coordinate system, say an X and Y coordinate system, and we could identify the coordinates of this point, and just for concreteness, I'll say that it's got the coordinates 4 in the X direction and 3 in the Y direction. So we could write this as X comma Y equals 4 comma 3. Okay. We also are able to define so-called unit vectors. So the X hat vector and the Y hat vector are unit vectors. And the word unit here means length 1. So this is a vector of length 1 pointing in the x direction for x hat or pointing in the y direction for y hat. So another way that we can write this vector A is that we could say A is 4 x hat vectors plus 3 y hat vectors. In other words, if we took 1, 2, 3, 4 of these x hat vectors and then 1, 2, 3 of these y hat vectors, we get to the same location that we would have if we just went from the origin directly to that final point along the blue arrow A, okay? So we have another way of writing A as just 4 x hat plus 3 y hat. And here, these unit vectors we can think of as our basis vectors. So we can write the vector A as a linear combination of x hat and y hat, okay? And if we think back to this example of the intermediate state as being 1 over root 2 of plus x and 1 over root 2 times minus x, we can see kind of a direct analogy here. The state is the vector A, here the intermediate state, is a linear combination of x hat and y hat basis vectors. Here it's a linear combination of plus x and minus x basis vectors, and the coefficient tell you how much of each basis vector you need to make up the actual state. Okay. But just as in we saw that we can write the intermediate state using multiple different bases, we should be able to do the same in the geometric example as well. So let's see that in action. So here we have our old scenario, and here's a new scenario. We have the same A vector, okay? But this time we're going to decorate or add a coordinate system to this drawing, but we're going to add a different coordinate system. In this case, we are adding a coordinates where the new x-axis that I'll call x prime points straight up, and the new y-axis that I'll call y prime point to the left, okay? And the question is, well, how do I write down this A vector using my new basis of x prime hat and y prime hat, okay? So first of all, where are these vectors x prime hat and y prime hat? Well, they point along the directions x prime and y prime. So x hat prime points straight up, its length is 1, and y hat prime points along the y hat direction, the y prime direction, and it also has length 1. And so if we want to go from the origin to the tip of A, we would now go up 1, 2, 3 of these x hat primes, and we'd have to go backwards 1, 2, 3, 4 of these y hat vectors, y hat prime vectors. So right now we know these coefficients are plus 3 and minus 4. So we have to change that plus to a minus sign, because we actually have to go minus 4. And we can erase these underlines here. And so now we have a new way of writing the same vector. So these are equivalent because they're describing the same blue arrow. You could either write it as plus 4 in the x hat direction and plus 3 in the y hat direction, or you could do plus 3 in the x hat prime direction and minus 4 in the y hat prime direction, but you're going to get to the same place in both cases. And notice this is exactly the same that we saw before. We could write the intermediate state of a silver atom coming out of the Z analyzer as either in either the x basis or the 10-degree basis. So here either in the x hat y hat basis or the prime basis. And the coefficients are different in the two cases, just like they are here, 4 versus 3 and 3 versus minus 4. But they represent the same state. Here they represent the same vector. So this was just a quick video to give a geometric analogy for what it means to have different basis vectors for a state of a quantum system. And we've seen that it's the same as using unit vectors to describe, to different sets of unit vectors, rather, to describe a 2D vector geometrically.